Yes, buenos dias. Yes, that is the question, and I'll try to offer several answers. In fact, one way of dealing with this, actually, when I received the invitation to talk at this meeting, I was asked to speak on the subject of PDRs, and the abbreviation was not spelled out. So, in fact, I didn't know whether to title this Photodissociation Regions or Photon-Dominated Regions. And as I got further into preparing this talk, I tried to think a little bit deeply about what it really means and what we've learned since the concept phenomenon. But what I'm going to try to do today is to take you on a rapid tour through some recent developments that I have found interesting, and in particular things that I think point toward open questions that have not been properly answered or thought about. And so I'm going to do a kind of random walk through various kinds of photodissociation regions, or at least things where I recognize the characteristics of PDRs being important. So just as an outline, you can see the 3 or 4 topics that I'm going to cover. First, I'll start with just a little bit of introduction and background for those who may not be very familiar with what PDR stands for. First of all, a very important point is that in interstellar matter, dilute gas in general, it's very important that the physical and chemical state is typically very far from thermodynamic equilibrium. Okay, this is such an important point that I repeated in the second bullet. And part of what we learn from models of these photodissociation regions, the edges of molecular clouds, the boundaries between atomic and molecular gas, part of what we learn from the models is that these regions are stratified. So abundances, temperatures, other physical conditions often vary quite rapidly with depth, and that stratification makes them complicated. But again, this is largely because that the physical and chemical state is far from equilibrium. And what that means is that we can only describe these large structures in space in terms of microscopic processes. We must describe them in terms of microscopic processes. This is exactly what Cloudy addresses, and it's also the reason why Cloudy has such a voracious appetite for atomic and molecular data, right? Because we have to keep track of numerous physical processes and radiative processes. All right, typically in the photodissociation regions, ultraviolet radiation plays an important role. Sometimes possibly a dominant role, but it plays an important role in controlling the chemistry through photoprocesses, controlling the thermal balance through heating, and then, of course, the escape of radiation affects the cooling. Also, the ionization state, and so on and so forth. So and it's often ultraviolet radiation. We'll talk about other parts of the electromagnetic spectrum shortly. The reason that PDR have attracted so much attention in the last several decades is that we now know from observations, especially in the far infrared and submillimeter parts of the spectrum, that the PDR regions, these boundary zones between atomic and molecular gas, actually dominate the power coming out of star-forming regions, collective starbursts in the centers of galaxies, and so on. So they're often extremely luminous, and if we have the possibility to observe in the infrared and radio parts of the spectrum, they may be some of the brightest things that we observe in galaxies. Now, I think there are a few little identity crises. I don't want to dwell too much on this, but observations in recent years have added greatly to the sense of complexity. Higher angular resolution means that we see more details of structure, and that in combination with excellent velocity resolution, especially now in the far infrared and submillimeter parts of the spectrum, mean that we recognize even more about the chemical complexity of these regions and try to understand what that implies for how they are related to things like star formation and the evolution of galaxies in general. The other thing is that, in fact, I can show you here, by the end of the talk, you'll see that we go all the way from radio frequencies to gamma rays. And so a panchromatic view covering all wavelengths of the electromagnetic spectrum is an important part of how the observations have developed. In terms of the models, I'm afraid that the models are losing ground in their ability to cope with the complexity revealed by recent observations. Okay, and also I think sometimes if we talk about photon-dominated regions, although this is what I was indoctrinated with in my youth, you might say, to call PDRs photon-dominated regions, I now think actually that that's an invitation to prejudice the case in constructing models. And we'll see some examples of regions where photodissociation is undoubtedly very important, but the photons may not be the most dominant source of pressure ionization, various other things. Okay, I should now try to explain just very briefly what a PDR is. What is a photodissociation region? The boundary between atomic and molecular gas typically is controlled by ultraviolet photodissociation processes. And it's very important to notice that the physics of two molecules, H2 and carbon monoxide, are responsible for a lot of the PDR phenomenon. That is, there are only three simple molecules, H2, carbon monoxide, and molecular nitrogen, that are photodissociated in the ultraviolet longward of the Lyman limit of hydrogen through line processes, through line absorptions. All other molecules, simple and complex, tend to have continuous photodissociation processes, broadband absorption. The fact of a line-induced photodissociation process means that the absorption can saturate in particular at a rather small column density for H2 or CO, column densities of the order of 10 to the 14th per square centimeter. That means that in the layer of a gas cloud exposed to ultraviolet starlight, for example, the outermost boundary layer absorbs most of the photons that are able to photodissociate molecular hydrogen in a very narrow zone. As a consequence, there can be an extremely sharp boundary between atomic and molecular hydrogen. Now, even though the carbon monoxide is also photodissociated mainly by lines, and those saturate also, the carbon monoxide is enough less abundant that some of the shielding and the attenuation of the harmful radiation is accomplished by dust grains, and also by the hydrogen molecules and hydrogen atoms that compete with CO for the same photons. So the boundary in carbon monoxide may be smoother, and in fact, in some very interesting PDRs, the carbon monoxide may not be noticeable at all because it's fully dissociated or present in only very small amounts. Okay. When ultraviolet photodissociation dominates the structure of the boundary, then it's often the case that the UV radiation also dominates the heating, and primarily through the photoelectric effect involving dust and extremely large molecules like polycyclic aromatic hydrocarbons. Okay, this can raise the temperature of a typical PDR to more than 100 Kelvin, and it's exactly in this range of temperatures where the most abundant molecules and some of the prominent atoms and ions that persist. It's exactly in this range of temperature of 100 to a few hundred Kelvin where molecules and atoms shine very, very brightly at millimeter, submillimeter, and far infrared wavelengths. Okay, this is not a model. This is a schematic diagram of a low flux photodissociation region that is showing the diffuse and translucent molecular clouds, the low density gas that fills the space between the stars, but in very modest amounts, these clouds are possibly the remnants of star-forming regions that have already done their work, or material that is collecting once again into clouds that have densities greater than the average intercloud density. So again, here one can see a sharp transition. This is fractional abundance versus column density of hydrogen in all forms. A sharp boundary in the hydrogen, that is, the atomic hydrogen is most of the total until this point where the molecular hydrogen fraction grows to account for essentially all of the hydrogen. There will often tend to be a smoother transition to carbon monoxide, and in fact there can be a very large zone in which C+ and neutral atomic carbon coexist. Okay, the reason that I bring up the diffuse and translucent clouds is that some very interesting things have happened in the last few years, and in particular as a result of spectroscopy in the submillimeter and far infrared part of the spectrum, and especially as a result of the Herschel Space Observatory, and in particular the HiFi instrument, the high-resolution heterodyne spectrometer on Herschel. These observations have led to not only discoveries of new molecules, some of which were long anticipated, but also surveys of these molecules in absorption lines at submillimeter wavelengths. Here, compact, bright star-forming regions are used as background light sources for absorption measurements. And because these can be seen across the entire Milky Way, we get now very large, very long lines of sight through the interstellar medium. And some of the new discoveries include the discovery of hydrogen fluoride, which is an excellent indirect tracer, a surrogate for molecular hydrogen at low molecular fractions. OH+ and H2O+, which have long been thought to be part of the backbone of the interstellar ion neutral chemistry, and now have been observed so that the chemical models can actually be confirmed directly. SH+, which, like CH+, probably traces superthermal chemistry and perhaps even in, generally speaking, in turbulent dissipation regions, as well as several nitrogen hydrides, which show that in the diffuse and translucent gas, the relatively low density gas, the abundances of NH, NH2, and NH3 are comparable to each other within a factor of 2. As a result of large surveys, it's also now been recognized that there is a large amount of CO dark molecular gas. That is gas that may have a large molecular hydrogen fraction, but not enough carbon monoxide to produce CO emission lines at millimeter wavelengths that exceed the detection limits of typical large-scale surveys. So this material doesn't show up in the large surveys of CO, but it's an important component of the neutral and molecular interstellar medium of the galaxy. also, in particular, because reactive molecular ions like OH+, H2O+, and H3O+, can be observed now, we have some excellent probes of what cosmic rays do. And for molecules like SH+, and CH+, we can probably infer something about the dissipation of turbulence in these regions. Okay, and this growing amount of chemical detail then provides excellent tests of molecular models. So are these regions studied by absorption lines really in really molecular clouds or not? There are some cases where it's actually possible to trace here the contours of brightness of carbon monoxide emission and find that there is a molecular region that is well isolated in projection on the sky. We've already known that a cloud can be recognized as a well isolated component in wavelength or Doppler velocity. It's an isolated velocity component. This is a very old carbon monoxide map dating back to the 1980s, late 80s. But the direction of this star is still a very interesting place to look for absorption lines. And so just within the last year or two, finally convincing evidence for fullerene ions has been presented, and this is one of the places where they were first recognized. So these absorption features are diffuse interstellar bands in the far red, and they can definitely be attributed to C60+. That has been confirmed by beautiful laboratory experiments. Likewise, this cloud also shows an array of smaller pure carbon molecules. In this case, C3, the red curve shows the astronomical spectrum, and the blue curve shows a corresponding laboratory spectrum of the same C3 absorption band. Okay, I'm probably going to have to start skipping slides at a faster rate. This is just another example where one can see in the mid-infrared emission from PAHs. This is actually the star with this HD number that is used as the background source for these absorption spectra in the ultraviolet here, and then some absorption spectra in the visible that show molecules like OH+, NH, C3, and even atomic titanium ions. And it's also possible to observe 3 distinct velocity components in the carbon monoxide emission from the same cloud. Okay, one of the things that I think needs to be improved in the models, even of these simple, low-density, isolated molecular clouds, the diffuse and translucent clouds, is the input ultraviolet spectrum. It's been traditional to use models of the average background starlight to describe the input starlight spectrum. And here's one example. The dotted line shows the radiation field due to Bruce Drain in 1978. However, if you go through the exercise of simply summing up the old Copernicus high-resolution spectra of all of the brightest stars that were observed with that instrument, then you see that in this important part of the spectrum, going down to the Lyman limit, there is quite a lot of structure in the background starlight. The difference, but this is just a composite of observed spectra. The difference between the flux level and drains is a few of the stars that were not included in the sum because they were not directly observed with the same resolution, and also a contribution due to the scattering by the dust particles that almost doubles the flux that you get by simply summing the observed radiation from all of the hottest stars in our neighborhood. So to make a long story short, if we want to describe the background starlight spectrum at a typical point in the solar neighborhood, that is right here, what we observe directly, it's going to look something like this. It's not going to be a smooth, continuous spectrum. That means that all of the ensemble of thin interstellar clouds between us and all of the stars that contribute to this radiation have already taken out some parts of the spectrum. And so what the molecules in any particular cloud are exposed to also is a spectrum that already has structure removed from it. In particular, some of the flux that would otherwise photodissociate H2 at a higher rate than you would estimate from the smooth continuous spectrum. Likewise, there's another interesting feature. We grow up learning that the neutral interstellar medium is completely insulated from hydrogen ionizing photons. But in fact, that's not true. There are direct observations of a few of the very nearest hot stars, both hot white dwarfs and 2 or 3 B stars, that produce an extreme ultraviolet spectrum, again on the same flux scale as this, in the hydrogen ionizing part of the spectrum. It's enough to produce an unshielded hydrogen ionization rate of greater than 10 to the minus 15 per second. Now, of course, that's rapidly absorbed out in a very thin transition zone, but it does exist. Okay, just a little bit more about the wonderful discoveries from Herschel. It's been possible, this is a graph of the column densities of several interesting molecules and atomic hydrogen as a function of radial velocity in the direction of the galactic center molecular cloud, Sagittarius B2. This is an estimate of the total molecular column density per unit velocity in kilometers per second. So that's why the column density looks a little bit low. This is the velocity distribution of the H2O plus absorption, and this is argon hydride plus. You know, another fact that we were taught in high school chemistry courses was that the noble gases do not form molecular bonds. Well, that's also incorrect. We do actually observe molecules, molecular ions, that contain noble gas atoms, argon hydride plus. Not only that, it's widespread in velocity in this direction, and as we see on the next slide, the argon H plus is detected in almost every direction that we were able to look in the Herschel data. Not only that, now that, although this is pretty far into the submillimeter part of the spectrum, the argon H plus is not directly observable from the ground because of atmospheric absorption. With a significant redshift, like 0.89 in this case, the argon H plus frequency is redshifted into something that is accessible with ALMA. And indeed, we have succeeded in detecting the argon H plus and many of these other exotic molecules in a galaxy far, far away, where we can also study now diffuse and translucent molecular gas, and we find that many of the relative abundances of the molecules are very similar to what we observe in the Milky Way. Not much chemical evolution in that case, out to a redshift of almost 0.9. The ion chemistry shows how cosmic rays on H2 or on H get propagated through oxygen-containing molecules, and as a result, the abundances of OH plus and H2O plus are excellent tracers of the cosmic ionization rate. Together with extremely simple chemical models. And as a result, it's been possible to build up a large enough sample, both based on Herschel observations and on ground-based observations of H3 plus, to be fairly confident that the typical cosmic ray ionization rate in the galactic disk is about 2 times 10 to the minus 16 per second per hydrogen. Okay, I think I'm going to skip that. It's a very interesting detail about the use of H3O plus actually to estimate directly the rates at which chemistry is happening, because we can see the results of the chemical formation of this ion in the population of excited metastable states. Okay, we gain quite a lot in our knowledge about the Milky Way when we combine spectroscopic observations with other kinds of data, and in particular, observations of the thermal emission by dust throughout the galactic disk and even gamma rays. It turns out that this is one of the beautiful ironies of physics and molecular astrophysics, and that is that the biggest, coldest, and darkest places in the galaxy can also shine brightly in gamma rays. And that's because cosmic rays interact with any nuclei, but in particular with the hydrogen, in these big collections of hydrogen in gas clouds, and produce gamma rays through the production of neutral pions that then decay with the emission of gamma rays. So that's responsible for the diffuse gamma ray glow that we see surrounding all of the gamma ray point sources, which are of interest to the high energy community. Okay, but by combining all of this kind of information, then it's possible to make now an assessment of how much of the neutral gas is not traced by carbon monoxide when these other observations are also compared with the existing carbon monoxide surveys, the emission line surveys at millimeter wavelengths. And much of that can be attributed to these diffuse and translucent molecular clouds. All right, so here just one other comment about these points. The photodissociation regions, I think, are real here, and they represent places where there is at least some molecular hydrogen, but where the UV starlight is setting the boundary between that and the atomic and ionized gas. But at the same time, these are not completely photon-dominated regions, because other agents, especially the cosmic rays, have a very important role to play, especially in the chemistry, some of the ion chemistry, but also in some of the very interesting ways that we have to sense these regions. Okay, I wanted to make a few quick comments about the wide range of scales on which we see PDRs in the same part of the sky, in Orion. And I'd also like to remind us that this whole subject of PDRs really got going when Xander Thielens and David Hollenbach first presented the concept of the high flux photodissociation regions and pointed out that they should glow very brightly in the far infrared and submillimeter and add lines to the very intense glow continuous glow of the warm dust particles. And this is a flashback to 1989, and it shows that even the 1985 vintage Thielens and Hollenbach models actually reproduced rather well the observations that existed at the time, mostly of a few of the very brightest PDRs like the Orion star-forming region. Okay, since that time, the PDR models have accreted much more physical detail, and especially through the implementation in cloudy, have become much more flexible so that they can deal with the wide range of environments that we find them in. But much of the insight already dates back to the 1980s. Okay, this is a close-up from a recent paper that just appeared last year, led by Javier Goicoechea, based mainly on beautiful Herschel observations with HiFi at high spectroscopic resolution in the carbon-2 fine structure line at 158 microns wavelength, or 1900 gigahertz something. And together with some ground-based observations of the H41 alpha recombination line that is extinction-free and traces the purely ionized gas. The ionized gas, it has the greenish tint. That's the famous H2 region. The blue coding represents the carbon-2 line, and the red represents what comes from the fully molecular zone, or the deeper parts of the PDR layers. That's the carbon monoxide 2-to-1 line. And so all of some of the very, very complex PDR structure in the core of the Orion molecular cloud and its exposed surface can be revealed just by comparing these different tracers. But taking advantage of the very high resolution in these C2 observations and comparing the line profiles of the three different tracers, a low ion stage tracer, a molecule, and a nebular tracer, then it's possible to do an even better job of isolating the different contributors to the total bright line and continuum radiation coming from the star-forming core of Orion. I had a few other slides just to illustrate, if we look on smaller scales, the arcsecond or subarcsecond scale, and look in particular at molecular hydrogen emission in the near-infrared, we see that this is concentrated in small knots of extremely high surface brightness. But if we go to larger scales, now if we inquire, what would we see if we observed the molecular hydrogen emission coming from Orion on a scale of 1.5 degrees? And this encompasses the entire nebular region and much beyond. Right? It turns out that the UV-powered fluorescent emission of molecular hydrogen completely dominates at the level of 98% or more, according to this very interesting study that was published back in 1994 by Kevin Luhmann et al. And that, I think, is a very important thing, because large-scale PDRs in other galaxies, I think, are also going to have this characteristic, that there is a large amount of very dilute or very extended PDR regions. Now, there are other interesting things that happen. Of course, the photoevaporation zones of proplyds, discovered by Bob Odell and his collaborators, are also kinds of photodissociation regions. And these are things that occur on the arcsecond or subarcsecond scale. And just a few examples of those I'll whip through. Also on small scales, there are very interesting comparisons that are done using cloudy models in particular to say something about the abundances in the material that has been evaporated from neutral gas that's embedded in the ionized nebula or close to it. Now, in the last few minutes, I want you to try to imagine what you're actually trying to model when you're trying to describe a starburst in the center of a galaxy. One of these things that is cranking out 100 or 1,000 solar masses per year of stars. Right? Imagine thousands and thousands of Orion regions crammed together in a small volume. We see this nearby and on a much milder scale with overlapping supershells that actually form new molecular filaments and sheets in the Magellanic Clouds. And there are becoming more and more interesting detailed numerical simulations of how molecular structures form in these regions. But these are also places where there is a fairly large density of very hot stars that illuminate their surfaces. So lots of PDRs there. Let's go to M82, a nearby starburst galaxy. It's actually a modest luminosity starburst, but it's nearby and extremely well studied. This is a recent paper by one of our PhD students in Sweden, Eskil Varenius. Yes, my time is running out quickly. You can probably see a few little dots in this fuzz. This fuzz is just the synchrotron radiation at 154 megahertz from the relativistic electrons. That's one form of cosmic rays in the center of M82. These little dots, each one of these is a rapidly evolving supernova that has gone off within recent memory or an extremely young supernova remnant. So we actually have the possibility now of doing a census of the supernova explosions that take place in starbursts. And we have some ways of this, in the last 1 minute or so, scale this up to ARP 220, where my colleagues are able to count dozens of supernovae, recent supernovae and supernova remnants, to infer the supernova rate and the density of these objects that are energizing a very small region, a place where there may be something like 1 million luminous hot stars inside a volume of radius 50 parsecs, but also, likewise, in that same volume, there are hundreds of recent supernova explosions with interacting shells and so on and so forth. Okay. This gives rise to all sorts of things, and I will jump immediately to the summary. I've tried to, well, it's been said that my train of thought often takes the scenic route, and I hope it hasn't gone completely off the rails. But, whoosh. Okay, yes. But I've tried to give you some indication of recent developments in the variety of photodissociation regions that we have, and a sense of the enormity of the challenges that face any attempt to model these things, especially in phenomena as complicated as nuclear starbursts in galaxies. Thank you very much.
We have time for a few questions. How do you know about the C60? About the C60 plus interpretation of the DIBs, what fraction of the diffuse interstellar bands are identified now?
I think these 3 lines. Xander may have more to say about this.
I think that's
yeah, I think it's only this is the one, I think, absolutely convincing identification. And I believe at this point there are no others. It's very likely that the carriers of many of the others are the same sorts of large carbon molecules. But
Nick?
So ARH plus has been discovered. Has there been searches for like neon NEH plus? Is there any?
I think some of our Herschel data covered neon hydride plus. Yeah, we actually addressed that in the paper, I think, again with simple chemical models and knowledge of some of the reaction rates. It can be explained why the neon H plus isn't as abundant. The argon H plus is special because there is a formation reaction that goes at low temperature, and the same is not true with the neon H plus. I think the best place for looking for that and also for HEH plus might be in the molecular tori around AGN, where there might be molecular hydrogen exposed to such a high ion